All right, welcome to Physics 1 Quarter 2. I'm excited to be working with many of you again. And so hopefully this class will look very similar to Quarter 1 and you'll be able to jump right in. Those of you who are new to working with me and taking Physics 1 Quarter 2, this is pretty much how every class is going to be. I'm going to have a video that will explain every lesson, and every assignment will be through Go Formative. And the whole point of that is, one, I can give you quick feedback, and two, you get in a routine and a habit of how to submit and get that feedback. And pretty much every activity, you'll have the opportunity also to go back in and improve or make changes. So in class, you'll have time to ask questions and get help, and then improve on your assignments. So that's the whole goal. Again, if you're new and have any questions, please talk to me in class, whether through the private chat or during the question portion of class. So getting started with Quarter 2, we are transitioning from motion, where we talked about velocity, and constant acceleration, and distance and time, and how that all related. Now we're really going to be talking about forces, but we're going to learn that forces really is related to motion. So we're going to have, I would say, fewer calculations and more conceptualizing of what these forces are and how to model forces to make predictions. So again, similar to before, we were making calculations around motion to make predictions, and now we're going to be thinking about the forces that are going on in order to make predictions. So this activity is going to introduce what is a force, which hopefully sounds familiar. Hopefully you've learned some of this maybe, and some of it sounds familiar. And we're also going to introduce Newton's laws of motion. So you're going to have 10 questions below that are all related to the Newton's laws of motion. So again, I'm introducing you to them now, and then you're going to have a few questions to see if you're understanding the concepts. So from the start, here we are. What is a force? A force is a push or a pull. So literally anything, whether you know the name of it or not, okay, whether you know something like gravity, but it is a push or a pull. And so when you think about that, okay, well, if something is pushing or something is pulling, that's motion, right? Something is moving. So then we're going to talk about a net force. And so the net force is the combination of all forces acting on an object. The net force on an object changes its motion. So something to consider. If the net force is 0, okay, this hand is pushing against this hand equally. If the net force is 0, then there's no motion. The object is going to be basically forced to sit still. But if there is a net force in any direction, then there is going to be movement. Equilibrium, to go back to the net force, whenever the net force of an object is 0, the state in which no physical changes occur. So again, so this would be considered equilibrium because both forces are equal, and therefore the net force is 0 and no changes happen. That's equilibrium. And the unit of measurement, this is going to be new to us. We've been talking about units for distance, units for velocity, units for acceleration, units of time. Now we're going to talk about the units of force. And the good news is there's only one, and it's Newton's. So we're going to get familiar with Newton's, and it is represented by a capital N. So some common forces that I think Most of you have probably heard of at least one or two or a few of these. So, gravity is the number one. We will talk about gravity a lot, as every scenario here on Earth, okay, that we can possibly look at has gravity. Okay, so this is a force that will always be present on Earth. So the universal force of attraction acting between all matter, most commonly referred to between Earth and objects on Earth. So, when we're talking about, gravity, our first thought is here on Earth. It does apply to everything in the universe, no matter where you're at in the universe. So if you're on a different planet, okay, the force of gravity changes, but it's still there. If you're in outer space, again, the force of gravity changes, but it still exists. And one of the universal laws of gravity that we understand is, again, it is an attraction between all matter, between every single atom. Okay, I got my water thing. There's a force of gravity between me and this water container. Okay, so between all matter. Now, we know that gravity is impacted by mass. Okay, so if you have a larger mass, you're going to have a stronger gravity, which is why Earth, because it's so massive, there's so much mass. Okay, it's actually not size. I should re-say that. Because there's so much mass of Earth, that there's a larger force of gravity. But then it's also distance, which is why when we go away from Earth and get further away, the force of gravity between us and Earth becomes weaker and weaker. So hopefully that might sound familiar from maybe 8th grade, but that's a little synopsis of gravity. With friction, it's a force that pushes in the opposite direction of an object's motion when two objects touch. Okay, there is friction between my hands. My hands are touching, they're going in opposite directions, and therefore friction is present. We use this with our shoes. Okay, if you have a lot of friction in your shoes, you have good grip, right? And that's kind of another way we say it. If you don't have good friction between your shoes, then you have weak grip or not very much grip, and you slip. Uh, and so some objects will have more friction, some will have less friction, and friction will often be part of our scenarios as well. Then there's something called a support force. This is something less commonly talked about, but it is the upward force from a horizontal surface, and the support force must equal the object's weight. So that's actually very interesting. I don't know if you can see down here my table. Okay, if I push down on the table is supporting my finger. Okay, it is pushing against my finger. What you can also see is why my finger kind of starts to bend. And then the force in which I'm pushing down is the exact same force that the table is pushing up. So that is the support force, and it is always going to be equal to the force pushing down on it. If it's not, then the table is going to break. So keep that in mind. A tension force. This has to do with string or a spring. So we call this a stretching force present when string, rope, or springs are involved. So the tension force must be equal also to the object's weight. So very similar. When you think about maybe the springs in your suspension on your car, okay, there's springs on every tire or wheel, and that tension is equal to the weight of the vehicle being pushed down on it. So that is an example. And then drag force is also common. And the drag force is the resistance of force caused by the motion of a body through a fluid, such as water or air. So this really, drag force summarizes air resistance. When you go through air, you are getting hit by particles of air. And that in some aspects is similar to friction, but it's resisting your motion. And the faster you go and the bigger you are, we see that there's more air resistance. Uh, and then similar with a body of water or fluid. Okay, so you go swimming through water. It is due to a drag force that you can actually propel yourself, but it also slows you down. And so you'll see professional swimmers uh, try to make their body as smooth as possible to reduce the drag force when they're swimming. All right. So again, there are hundreds of more different forces. These are the common ones that we have names for. So that will kind of give us a little concept as we think of these scenarios. Then we have Newton's laws of motion. Some of these we've already talked about. Some should sound familiar from possibly previous learning in middle school. But Newton's first law of motion says an object at rest will stay at rest, and an object in motion will stay in motion unless acted upon by an unbalanced force. So, again, that's relating to that net force. If there is a net force, then it might speed it up or slow it down, that kind of thing, right? There's going to be motion. But so an object at rest, again, hopefully you can see this. I put my phone on the table. I fully expect it's just going to sit there. And the reason is we know that the support force going up and the force of the weight due to gravity is pushing down. And we know, based on what we just learned on the support force is always equal to the weight. So this is a balanced set of forces. And therefore, we know that it's just going to stay there. We could sit here a very long time watching my phone, and you know it's going to stay there. That's something you're familiar with. You set something down, you expect it to sit still. So the opposite, though, is true. An object in motion will stay in motion unless acted upon by an unbalanced force. So this is something we don't see on Earth very often because there's always an unbalanced force when something is going in motion, like friction or drag. And so you throw a baseball, okay? Ooh, and gravity. There you go. So you throw a baseball, it doesn't go in a straight line forever and ever and ever. Gravity pulls it down, air resistance slows it down, and therefore you have these unbalanced forces that are acting on it. In outer space, there is no air resistance, and gravity is very, very weak. So in outer space, we have hundreds of thousands of millions of billions, trillions of examples. So an orbit, right? Again, hopefully, maybe this sounds familiar. Orbits are only possible because their motion never slows down. And so, therefore, they're always going to continue moving. And that is due to this first law of motion, also known as the law of inertia. We do see inertia here on Earth in small forms. And one of the most common is when you're in a car. Okay, you're driving and you have to slam on the brakes. When you slam on the brakes, the car, with its friction and its tires and its grip, slows down, and the tendency of the passengers with our seatbelts is to fall forward. That's your inertia, that first law of motion, that your body wants to stay in motion. If it weren't for the seatbelt and it weren't for the brakes, you would just keep going. And unfortunately, in some aspects, you're not wearing a seatbelt, then it can be quite serious of a problem. Okay, Newton's second law. This is the one we're going to focus the most on as we continue through this unit. But it's talking about the acceleration produced by a net force on an object is directly proportional to the magnitude of the net force, is in the same direction as the net force, and is inversely proportional to the mass of the object. Again, that doesn't necessarily make a whole lot of perfect sense, at least to me, right? You read that and you're like, what is it saying? But what it's describing is the mathematical equation. Okay, acceleration is equal to net force divided by mass. And so this then you can describe as a relationship. And we can use mass and acceleration to find the amount of force. And some examples with sports and different things. Again, let's say a football player with more mass going at 5 meters per second is going to have a greater force than a football player that's smaller going the same speed with that acceleration, I should say. Okay, so we can then calculate mass times acceleration to find our force. Something also, a little note with this, if you know the mass in kilograms, so we're going to be using kilograms more often, mass of an object on Earth, you're going to multiply it by 9.8. That might sound familiar from our previous activity. That's the force of gravity, or the acceleration due to gravity. And so, again, that would be our acceleration, 9.8 meters per second. So if you have a 1 kilogram object, okay, which might be something like a cell phone, okay, 1 kilogram, it is going to have a downward force. So again, we're not talking about newtons, we're not talking about weight, but a downward force of 9.8 newtons. So now we can talk about the similar scenario in terms of force by knowing the mass and the acceleration. Newton's third law, and this one is pretty commonly talked about. I think it's very simple to read and maybe understand, but I also have a diagram here. So Newton's third law, for every action, and in this sense it's going to be force, for every action there is an equal and opposite reaction. So this is very interesting, but again, you have a person here, and their weight, their mass and gravity creates this F2. That is the force pushing down. And the Earth pushing back up is F1, and they are going to be equal. Other examples, okay? You maybe if you are in the fighting world at all, like mixed martial arts, anything like that, okay? You go to punch something. It could be a brick, it could be a wall, it could be somebody else if you're in a competition perhaps, okay? You go to punch them, well, it doesn't just hurt whatever you're punching, it hurts your hands pretty significantly. And so the reason is right here in Newton's third law. The force that I've put into this object is also received on my own fist. So Newton's third law is very important with that as well. Next, I have a little note about modeling forces. Modeling forces is going to be called a free body diagram. And so I'm going to refer to it as a free body diagram, but the most important thing is that you're using what are called force arrows to represent the strength and direction of the force, okay? And so a couple small notes, and I think a lot of us have seen these before, so it should sound hopefully like it makes sense, but the length of the arrow is going to correspond to the strength. So if you have a really long arrow, that means you have a bigger force. And if you have a small arrow, then that's going to be a weak force. Then the direction. If the arrow is pointing that way, then the force is pushing or pulling that way. If the arrow is going that way, then it's pushing or pulling that way. And it can go in any direction, right? In a full circle, depending on where it's getting pushed or pulled from. And again, then these force arrows, one, you can calculate the force to them, but you can have some models that have the force labeled, but you can also have it without the forces labeled. but they're used by scientists and engineers to make predictions and predictions of motion based on the forces. So that leads us right to our questions here. Number one, what is the net force in the following free body diagram? So again, we have these arrows that represent that these forces are pushing up. And so again, this would be a rope or maybe a chain. Okay, if you've ever seen those construction workers and that they're hanging on these kind of rafter things. So this would be a tension force and has 275, 275. Then we have this beam that the construction worker is standing on, and the downward force, so this would be due to gravity and weight or the mass of that object. So that is 300 newtons. And then the person is 250 newtons. So you have two forces pulling down, you have two forces pulling up, and you have to determine what is the net force. And so the little hint is if they're in opposite directions, they cancel each other out. So if they're in the same direction, you can add them together. And if they're in opposite directions, then you subtract them. Okay, and then you'll be able to find the F net, which would be the net force. Then, what forces are present in the scenario from question one? I kind of gave us a hint, okay, on a couple of them. You have a downward force as a result of a type of force, and you have an upward force, which is the opposite. And so you can determine what those would be. Then, again, explain what will happen. You have two individuals pushing against a movable wall. You want to use the force arrows to help you answer that question. Then I'm going to ask you to try and create a free body diagram. You've seen now two examples of a free body diagram. Can you draw one, including the force of gravity and support force of you sitting in a chair? And you don't need to try to calculate newtons or anything like that. Just focus on the arrows. And then I want you to try and create another one, and I'll give you like 3 scenarios to choose from. So person parachuting out of a plane, person walking down the sidewalk, or a skateboarder skating down a ramp. And then I want to just see what you come up with. Can you think of all the possible forces in this situation and include them in your diagram? Then I have a couple check for understanding type questions directly from the notes above. Okay. And then a little calculation problem. Okay, and again, I give you the formula. That's also from above. Force equals mass times acceleration. So I give you mass, and I give you the rate of acceleration. And which one is going to have a greater force? I do want you to show your work on that one. And then this one, if you set a textbook with a mass of 2 kilograms down on a table, force of the textbook pushing down is 19.6 newtons. What is the support force pushing up? Again, all these are conceptual other than this one, okay? That is just a basic multiplication problem. So I'm really trying to figure out if you understand the information up here. If you have any questions, please let me know. And again, I'm excited for quarter 2.